theorems. I'll tell you about that if I have a chance. Hopefully I'll have time to tell you about my experience. Not so pleasant experience, but what does it mean for a function to be differentiable in the closed interval from a to b? Many. Okay, so the limit has to exist, you said, of the function at every single point. And it's got to be, well, I don't want to give that away. So not only does the limit have to exist, yeah. There you go. That's what I'm talking about. Yeah, and to be continuous, the limit does have to exist and has to equal the functional value for every point in that interval. No corners or cusps, no vertical tangents, so nice and smooth. What's going on here? All right, so before we get into today's lesson, let's talk about the homework. I'm just going to slide this up. Slide that down. No. I should pause it. I think my lights here. So how's it looking, guys? All right, or not so good, huh? Oh, Leslie Hawkins is getting them all right, which is amazing. She wasn't even here yet. What? Yes. I'm looking at the Friendsgiving picture right now. Oh, that's, yeah, no. Oh, that's beautiful, actually. God, everybody's so beautiful in that. Let me see that. Oh, that's so nice. I wish you could see that, people. I'm looking at a picture. Kids. Okay. I'll just have to say to them about that. All right. Sorry, people. All right, so what do you want to go over? You want to go over some of these? What's the 14? 11? All right, you said 14, 6, 9. I heard 11. All right, let's look at 11 first, since that's the first one I heard. Okay. So in 11, well, let's see if you got the derivative right. So you had to, did you use the product rule? Oh, first times derivative of the second, because it's a product. Yeah, and you know, so when you take the derivative of the square root of 18 minus x squared, it's 1/2 18 minus x squared to the negative a half times the derivative inside, negative 2x. So the half and the negative 2 and the negative 2x cancel each other out. And then plus second times derivative first. But here's the thing which I think made some of these questions real tough. You go to take the derivative, and they involve fractions, but there's more than one term. And when that happens, it's much easier if you can consolidate them, get a common denominator, and put them together, add them. So you see, like, so I have these two terms, but it involves a fraction. So what you want to do is write them both with the same denominator. So you see how I could rewrite the second term with the same denominator? What would I multiply by? Nope. Just rad 18 minus the rad square root of 18 minus x squared. I wanted to have the same denominator as the other term. You see that? And whatever you multiply the denominator by, that's what you multiply the numerator by. So once they have the same denominator, you can combine them. And you might say, well, why do I want to go through that? Well, critical values occur when the derivative is either 0, so when the numerator is 0, or when it's undefined, when the denominator is 0. When you combine them like this, it makes it easier to see when it's 0, when it's undefined. So to get your critical values, you set your derivative equal to 0. So you look at the numerator. You set it equal to 0, you see that's when x is 3 or negative 3. When you set the denominator equal to 0, don't worry about that square root. You can just square both sides. So 18 minus x squared equals 0, when x equals plus or minus rad 18 or plus or minus 3 rad 2. So wow, so many critical values. That's crazy. Then we have to find the y coordinate at each of these. We have to take each of these and plug them into the original function. And you get negative 9 when you plug in negative 3, positive 9 at 3, and 0 for the other two. And those are just your critical values. Then you got to still find the value, the y coordinates at the end point. So you have to plug in the negative 4 into the original and the positive 4. So then you have all these y coordinates to compare. And when you compare all the y coordinates at the critical values and at the end points, the greatest of all these is 9. So that's your absolute max, which occurred at x equals 3. And the minimum of all these values would be the negative 9, which occurred at negative 3. So I don't think the concept's so bad, but it's just all the math and putting it together, setting the numerator equal to 0, the denominator equal to 0, solving. Someone's running around the room. Other questions? Is that all right? Okay. Okay, and I heard a 14, was it? I don't know if, I know people try different ones. Where's mine? I might not have 14. We'll just do 14. Okay, so 14, yowza. The function is x plus 8 over x. We want to find the max and the min on the interval from 1 to 8. So let's get the critical values. Let's get the derivative. So we take the derivative. What's the derivative of x? And what's the derivative of 8 over x? That's 8x to the negative 1. So it would be negative 8 over x squared, right? Because it's negative 8x to the negative 2. Okay, and we want to get the critical value. So we want to, again, there are two terms. One's a fraction. Let's combine them. So what would the common denominator be? X squared. Oops, so this, if I want to write the 1 over x squared, we multiply by x squared over x squared, so that one wasn't too bad. And now we can combine these. So our derivative is equal to x squared minus 8 over x squared. Now, critical values occur when the derivative is 0, so when the numerator is 0, or when it's undefined, when the denominator is 0. So let's set the numerator equal to 0. X squared minus 8 equals 0. If you solve for x, what do you get? Plus or minus rad 8, plus or minus, you could break that down a little. So plus or minus square root of 8 can be broken down, right, kids? Yeah, 2 rad 2. Okay. That's where the derivative is 0. But we also have critical values when it's undefined, when the denominator equals 0. Right? And that's when x equals 0. So I have 3 critical values, and I want to get the y coordinate at each one of them. Oh, this one is not even in the domain, is it? The 0. Okay, there's no way we can have a max or a min at a point that's not even on the graph. You see that? 0 is not in our domain. So we can forget about it. So we at least don't have to plug that in. We're not going to have a max or min at a point that's not on the graph. Okay? So really all we have to do is plug in the positive 2 rad 2 into our function and the negative 2 rad 2 into our function. Those are candidates. Okie dokie. So if I plug in, the function is x plus 8 over x. So it's going to be 2 rad 2 plus 8 over 2 rad 2. And this one is negative 2 rad 2 plus 8 over negative 2 rad 2. Do we just feel like leaving it, or do we want to do anything with that? All right, let's leave it. Okay, now, so we found out the y coordinates at the critical values. What else do we got to do now? The endpoints. So we just want to plug in the 1. So we have to get f of 1, and we have to get f of 8. Oh, I was going to shoddy the 1, but they're just as easy. Both of them are very good to do. What's f of 1? You could do that. Plug 1 in. 9. How about f of 8? 9. The only thing is, because now we want to compare all these, so we would kind of want to know 2 rad 2. Oh, that's annoying. I don't know. What's that? Well, I want to see, you know, what's the max and what's the min. Do you have any idea how great this is? Tell me. Yeah, just do that. I mean, or else we got to combine them, try to get an idea. So we're just picking out the maximum and the minimum value. I think that 9's going to still win out as the max, I think. And the min will just be the opposite. So well, this will be the min, because the other two were both 9, right? So that's going to be our min, whatever it is. And the max is the 9. Got it? Now, if they just say, what is the maximum value of the function, you can say 9, but I always like to cover myself and say at whatever. And it does occur at 2 different values, right? I would say both. I would say the maximum value is 9 at x equals 1 and x equals 8. So, not bad. So you want to hear a story? You want to know why I got into calculus? No, actually, it was because I wanted to fight a cop. That's, yeah. All right, so let me tell you my little story. All right. Can't go anywhere. So. All right, so everyone knows I used to be a trucker for Walmart, right? So, all right, so I had to, yeah, so I was a trucker, and what? Well, I wouldn't go, you know, from state to state. This route was actually, I was going from New Jersey. I think I was going to Vermont, but I had to get on the interstate. Anyone ever go on the interstate before? You pull up to a little booth, and when you get on it, and they give you a little ticket, right? And it tells you how much it's going to be, depending upon what exit you get off. You ever see those? So I get on, you know, I'm at this little toll booth. This little guy here smiles at me, right? I'm feeling good. I take my ticket and I'm on my way. That was the guy. I remember what he looked like. He didn't have a neck. That's why I remember what he looked like. Yep. So, but I was in a rush. You know, we're under pressure. So I'm driving down the interstate, and I got my radar detector on, and I'm looking around. It's not going off. So, I'm looking. It's nobody around. So I start, you know, speeding up a little bit. And I'm good, though, because I know nobody saw me. And then I get off, and I go to, you know, I take out my money, and I go to pay, and the attendant there says, "Can you just wait right here, please?" It's all right. What's this going to be? And this cop comes around the corner, and he says, "You were speeding." I was like, "No, you didn't catch me speeding." He goes, "No, you were speeding." I said, "What?" He goes, "Mean value theorem." Mean what? This is what he... You had heard of that? I was so mad. I never heard of this, right? Actually, what's that? The cop was angry. Yeah. So I said, "Wait, no way am I going to pay this. You didn't see me speeding. I know you didn't get me." And so On the when I got on there, it was 1:32 p.m. right, and I got there and I gave him my ticket to stamp, and it was, I believe, yeah, it was 2:02. No, 3:02. I remember that. No, it was 3:02 p.m. And the booths were 100 miles away from each other, right? So I said, I'm going to fight this. And he says, fine, it's the mean value theorem, go ahead. So that's when I had to start looking into what is this mean value theorem. And so he says, what was your average speed, your average velocity? I said, I don't know, but I know it was legal. And giving him an attitude because I really thought I was okay. So how would I get my average velocity? How, if you travel 100 miles and you start out at 132, okay, so you're going to take the change in position, so 100 miles. How many, because I want it to be miles per hour. I don't want it to be miles per minute. Okay, so 1.5. I want to stick to just hours. If you divide 100 by 3 halves, it's like multiplying by 2/3. It's 67 miles per hour. So, but how did he know? Just because my average velocity was 67, maybe I never went 67. Maybe I kept it under 65. That's what I was trying to argue. Is that possible? Well, see, this is what the mean value theorem says. It says, the thing is, if your average velocity is 67 miles per hour, didn't I have to go 67 miles per hour at least once? That's what the mean value theorem says. That at some point, and so, yeah, I got into that trying to fight it. I did not win, but I did get into teaching instead of trucking, so it's a really happy ending. How long ago? Yeah, it was, So just be careful of calculus when you're driving, kids. That whole... What's that? Did he? Well, a lot of people in teaching have trouble with the law, and that's why they get into teaching. So probably common. So, yeah. It hurts my feelings. All right. All right, so let's see what this mean value theorem, just so remember that mean cop whenever you hear the mean value theorem. Mean doesn't mean mean. What does it mean? Average, right? What the mean value theorem says, that as long as your function is continuous over a closed interval, so it's not, like your speed doesn't jump from one value to another, it's continuous, and it's got to be differentiable, so it's nice and smooth, no corners, cusp, or vertical tangents, then whatever the slope of the secant is, if you've got some curve from A to B, the average rate of change is the slope of the secant, right? The slope of that line. That's the average rate of change, is the slope of the secant. Mean value theorem says that someplace between A and B, the slope of the tangent has to equal the slope of the secant. And wherever that happens, they say C. So it's basically a guarantee that the average rate of change will equal the instantaneous rate of change at least once, maybe more than once. But there's no way you can have an average value that's not equal to the instantaneous value. Did you? Maybe it's everywhere. It's everywhere. Just listening. Here's a better picture. And I hope that you can just see that would have to be true. So the average rate of change, remember that's just the change of y's over change of x's. That's the slope of the secant. Has to equal the slope of the tangent at least once for some value c between A and B. And so we're going to do a couple problems where we're going to find out where this value c is for some examples. So our first example is the function f of x equals x plus 1 over x. We could break that up. Do you want to break it up or just leave it as is? Like, like we can break it up to x over x plus 1 over x. You know what I mean? Like, you can make this x over x plus 1 over x, or we can leave it like that. Leave it? Okay, let's leave it. Okay, I just want to make sure it's continuous on the closed interval. In fact, this function f of x is not continuous at one value of x. Where is this not continuous? 0, okay? But it's continuous everywhere else. There's no other value that's going to make the denominator 0. So it is continuous on the interval from 1/2 to 2. Now, we're not actually going to take the derivative, but if we did take the derivative, what would the denominator be? Yeah, it'd be x squared, right? Because you use the quotient rule. You have denominator squared. So for what values of x will the derivative not exist? 0. But that's not in this interval. You see that? So it's still the derivative will exist for all x's between 1/2 and 2. You just don't want to make sure, you want to just make sure that you don't have any holes or vertical asymptotes or corners or cusps or anything weird going on between the endpoints. Okay, now we're going to go ahead and find the value c guaranteed by the mean value theorem. So the first thing you have to do when you're asked to find c, the value c guaranteed by the mean value theorem, is get the slope of the secant. Find your f of b minus f of a over b minus a. Okay, so we're going what's my b for this problem? 2. So I need to get f of 2, right? It's just change your y's over change of x's. Minus f of 1/2 over 2 minus 1/2. I better write our function up here. Our function is x plus 1 over x. Okay, so what's f of 2? Three halves. Okay, ooh, this is going to be a fun one. Minus f of 1/2. So 1/2 plus 1 over 1/2. What is that going to be? 3. The denominator is 2 minus 1/2. 3 halves. Okay, so the numerator is 3. Can I cross out those 3 halves? Oh, phew. Okay, what's the numerator? 3 halves minus 3. So you have 1 1/2 minus 3. What's the numerator? Negative 1 1/2. Negative 3 halves, right? So you have negative 3 halves over 3 halves. Good. So the slope of our secant is negative 1. Now the next, we're trying to find out where the slope of the tangent line is equal to that. So we got to get the derivative. I guess we're going to do quotient rule since we didn't break it up, huh? All right, let's get the derivative. Loady high. Let's live all over denominator squared. Does that clean up any? What's the numerator after you distribute that negative? 1 or negative 1? Negative 1. So our derivative is negative 1 over x squared, right? So that gives us the slope of the tangent. We're trying to find out where the slope of the tangent equals the slope of the secant. So the next thing you do is you set them equal to each other. So you're going to take your derivative, negative 1 over x squared, and set it equal to your slope of your secant, which will always be a number when you do it. It'll be some fraction or whatever. How would you solve that? Yes? Okay, we can get a common denominator. You can cross multiply. Okay, we could do that. Like, in other words, write it with a denominator, and then, All right, so what do we got now? So negative x squared equals negative 1. Divide by negative 1, multiply by negative 1, whatever you want to do. So x squared equals 1. And so x equals plus or minus 1. Now the thing is with the mean value theorem, it guarantees there's going to be a value c between a and b. So are both of these answers, 1 and negative 1, between our values a and b? Do you remember what they? No. So which one gets the title of c? The positive one. I said which one? That was good. Yeah, I didn't mean it. So c is equal to positive 1 because c has to be between 2 and a half. It can't equal a half. It can't equal 2. Mean value theorem guarantees there's a number c, and at least one. You might get more than one answer, but at least one value. It has to be between a and b. Cool. Ready to try another one? It's awesome. Ooh. Does anyone know what this graph looks like? Like without going to a calculator? It's a parabola. Okay. Now, if I rewrote it like this, could you give me more details? Like, you're starting with y equals x squared. What does that plus 3 in there do to it? Move it left 3. So I already know what this parabola looks like. It's like our friend y equals x squared, but just moved, well, I made it kind of fat there, but left. Okay. Now we're trying to find the value c guaranteed by the mean value theorem on the interval from negative 3 to 0. So we're looking at from negative 3 to 0. What's the first thing I got to find? The slope. All right, so I'm going to have to, the first thing I have to do is find f of, I don't care which one goes first, but 0 minus f of negative 3 over 0 minus negative 3. I'm going to get the slope of the secant. I just drew in the secant. F of 0 would be 9, f of negative 3, 0. What are you guys getting for that? 3? Okay. That makes sense, right? So in other words, you've got this parabola. Between negative 3 and 0, the slope's changing. But the average slope, the average rate of change would be 3. That's the slope of the secant. Now we want to find out where the tangent line has the same slope. So what's the next thing I got to do? Good. Oh yeah, now we got to get the derivative. What is the derivative of this function? 2x plus 6. All right, so we got the slope of the secant. We found the derivative. What next? Set them equal to each other. That's it. So we want to know where 2x plus 6 equals 3, the slope of our secant. We want to know where the slope of the tangent equals the slope of the secant. Can't wait. What are you getting? Now, is that number between our a and b values, between negative 3 and 0? Yeah. So that's the value c they're looking for. So c equals negative 3 halves. And what that's saying to us is that if we drew a tangent line at x equals negative 3 halves, that tangent line would be parallel to the secant line, right? It's going to be equal. The slope of the tangent equals the slope of the secant. Instantaneous rate of change equals average rate of change. Now there's a special case of mean value theorem that has its own name, but it's really just one special case of mean value theorem. It starts out just like mean value theorem. The function's got to be continuous over the closed interval and differentiable over the open interval. But here's the added This actually makes it easy. It says f of a equals f of b. If you have a function, right, and the y-coordinate at a is the same as the y-coordinate at b, I don't care what the function looks like, what is the slope of the secant going to be? If the y's at the end are the same, you get the slope, change of y's over change of x's, 0. So if the y-coordinates at the endpoints are equal, you basically save yourself that whole first step, okay? Yeah, you're still going to have to get the derivative, but if they say find the value c guaranteed by Rolle's, you know the slope of the secant is 0. See that? Now, I used to think of it like rolling along. And then the other thing I used to think of, Rolle's, I would spell like this in my head. I would remember the O was really big to remind me that the derivative equals 0, right? Rolle's. So yeah, and basically if you think about a graph, as long as it's smooth and continuous, if the y-coordinate's the same at A as it is at B, doesn't it make sense that somewhere between there the derivative would have to be 0? It's got to turn around. That's all it's saying, right? So this is just one little case of the mean value theorem with that added condition. Oh, let's just see if we can do one of those. Yeah, it helps you to visualize these. Oh, I made this one. Well, this one example I have here, it's a polynomial if you multiplied it out, so it is continuous and differentiable everywhere. All right, so those, we're just going to like blow through because I have to go quickly. But I did want to check that the endpoints have the same y value. If you plug in -1, what does y equal? It's nice, it's factored. If you plug, you see how it's going to be 0? And if you plug in 3, what do you get for y? 0. So the endpoints have the same y value. So we can apply Rolle's. Again, all polynomials are continuous and differentiable. So all we have to do is get the derivative, set it equal to 0. And any answer between -1 and 3, that's our value c. Oh, who wants to get the derivative of that? What do I do? Should I multiply it? Oh, I'm not going to time. All right, first, I hope you're all thinking product rule unless you multiplied it out. You weren't? Oh my gosh. Times derivative of the second plus the second times derivative of the first. Well, you said it's easy. Oh, you have to set it equal to 0, but we could factor out an x plus 1. There's hope. If we set this equal to 0, we could pull out the x plus 1, and we'd have 2 times x minus 3 plus an x plus 1. Oh, we could clean up that second factor. So we have x plus 1, 2x, so this would be 2x minus 6 plus x plus 1. So the second factor would be 3x minus 5. Ooh, I hope that's right. Yeah, I don't know. So we had a common factor of x plus 1, right, with these two terms. Pull it out front because we're trying to find out where it's 0. Okay, so what values of x make this derivative equal 0? So when x equals -1 and x equals 5/3. Now, are they both between the endpoints? -1 and 3? Oh, they got to be greater than A and less than B. Sorry, you were so close, buddy, but you you can't be called C. Nope, the only C is going to be the 5. What is that? C equals 5/3. Yeah, because C has to be greater than -1 and less than 3. I don't know what that's doing. So that's the value C. All right. Oh, we didn't get to do one with trig. Oh, that's a shame. So your homework are these 5 problems. So, but both of these theorems, the function has to be continuous over a closed interval and differentiable over the open interval AB. The only difference basically is that with Rolle's is the endpoints have to have the same y value. F of A and F of B have to be the same. So have a great holiday. I'll say goodbye.